Okay, so today in this set of lecture notes, let's see if I can spit this out. Just going to be doing some linear algebra review. This is from section 7.2 and 7.3 in your differential equations book. And so in 7.2, we just define a few terms. So, what is a matrix? A matrix is really just, we usually denote a matrix by a capital letter. And it's just an array of numbers that has m rows and n columns. And so we would say that this is an m by n matrix. And so, it'll have all the entries here, m times n entries. And so when we talk about the ij position, right, that is the ith row and the jth column. And so we always go in the row column format. And so that's exactly the same as a spreadsheet. So if you're familiar with a spreadsheet, you can think of a matrix as just a subset of a spreadsheet. Okay, so we usually denote the ijth entry as something like aij. So that'll be a number. And we can perform some operations on a matrix that you may be familiar with. So some things, we can transpose the matrix. And so, for example, if A is equal to, we'll just do a 2 by 2 here. Oh, maybe a 2 by 3. A, B, C, D, E, F. Then A transpose is formed by taking the rows of A and making them the columns of A transpose. Okay? And so, in general then, if A is m by n, then A transpose is n by m. Okay? And so again, the rows of A become the columns of A transpose. Rows of A become the columns of A transpose. And so if you see the capital T, that's what we're talking about, is the transpose. Okay? Now, different from linear algebra, where we only dealt with real matrices, we could have complex entries. We could have complex numbers in a matrix. So, for example, 1 plus I, 2 minus I, 3, 4 plus I. Right? And so in that case, you could take the complex conjugate of A. And so the complex conjugate is just found by taking the conjugate of each number. Do you remember how to do those? So the complex conjugate. So if we have A plus, let me write it this way. If Z is equal to A plus IB, then Z bar is the complex conjugate of Z, and that's A minus IB. Good. And so the reason I say that, the reason we're bringing up the conjugate of the matrix is because when you're taking the transpose of a complex matrix, usually you want the complex conjugate transpose. And so there's a special symbol for that. A star is equal to A bar transpose. Okay, and so this is, if A is real, right, then A star, the adjoint of A is actually what that's called, is equal to A transpose. Okay. We're sometimes going to use that, so you may see this notation at some point. So that's why we're bringing that up now. Okay, so that's a little different from our linear algebra. All right. So Now we have the transpose and the complex conjugate and the conjugate transpose. Some other properties. What makes two matrices equal? When is matrix A equal to matrix B? Of course, that's going to be true if, and only if, Aij equals Bij for all numbers, right? I and j. Okay. And then what is the zero matrix? Right, that's the matrix with all zeros. Okay. How do you add two matrices together? Well, you add them element by element. That is, Cij, the ijth element of the result, is found by taking the Aij plus the Bij. Therefore, A and B must be the same size in order to add them. And then C must also be the same size as A and B. Good. How do you scalar multiply a matrix? That's also done element-wise, so that the result of this, the Cij, is just going to be the constant A times Aij. Right, so for example, if I have 1, 2, 3, 4, and then I take minus 1 times 1, 2, 3, 4, what do I get? Minus 1, minus 2, minus 3, minus 4. You just take the constant all the way through. Good. And that leads me to subtraction. So we define A minus B as A plus minus B, right? When minus 1 times B. Oop. Minus 1 times B. There we go. Good. So that's all straightforward. Multiplication is a little bit different. How do we multiply two matrices? Well, first off, I want to multiply a matrix times a vector, and then we'll define matrix-matrix multiplication. So how do we define matrix-vector multiplication? So if I take the matrix A times the vector X, right, then that's defined to be x1, that's the first element of X, times the first column of A, plus x2 as a scalar times a2, plus, let's call A, let's have A be m by n, right? And we'll have how many entries here? N of them, right? And so this is a linear combination. A linear combination of the columns of A using the scalars from the vector x. Good. And so, yeah, this is going to be an important definition later on. So it's always good to think of A times x as a linear combination of the columns of A. Good. Now we're ready to multiply two matrices together. And so that's done by taking the first column is A times the first column of B, and then it's A, B, 2. And let's see, is there any restriction on how many columns of B there are? No. So let's say that that's A times B sub P. Now if A is m by n, is there any restriction on how big the columns of B need to be? Well, the columns of B need to be n by 1, right? But then there can be P of them, so B needs to be n by P, and so this number has to match that number, right? And then the resulting matrix is what size? M by P. Good. And of course we know that it's defined this way because matrix multiplication is actually a function, and we'll talk more about that later. Very good. All right. And from this, by the way, you can probably see right away, or you remember it from linear algebra, that A times B is generally not equal to B times A. Only in special cases does that happen. Very good. So we're at the 10-minute mark. When we come back, we're going to be reviewing some functions on vectors, and then we'll talk about vectors and matrices altogether. See you then.